Okay, so for the first part here of Unit 4, Homework 3, we'll get going on this. So question 1, if the dot product of two non-zero vectors is 0, then the vectors must be perpendicular. Well, the dot product, right, we saw that in class. If you take two vectors and you do the dot product, then it says we take A times B, A dot product B times cosine of the angle between them. Well, if we know that A is not equal to 0 and B is not equal to 0, right, neither one's 0, then the only way that this total product over here can be 0 is if the cosine is 0, right? And we know that the cosine of 90 degrees is 0, which means the only way that's possible is if they are perpendicular. So the vectors do have to be perpendicular. So that is a true statement. So hopefully question 1 was pretty easy to work through. Question 2 here, also not too bad, just kind of a review of when is it positive work. And so keep in mind, positive work happens, right, when the force and the displacement are the same direction. So just kind of going through these 5 real quickly. As he picks up the box from the floor, right, as he lifts it from the floor, he's exerting a force upward, and he's lifting them upward. So that would be positive work. As he accelerates to a comfortable speed, so as he goes from rest, if he's accelerating this way, then he's exerting a force that way, and he's moving that way. So once again, for step 2 there, that would also be positive work, because as he accelerates forward, the force he's exerting is going forward, and the displacement is forward. Once he's carrying the boxes at a constant speed, right? Once he's carrying them at a constant speed, then the acceleration and the force are both 0, or the force that he's exerting is upward, while the displacement is right horizontally at a constant, but the displacement is horizontally, and therefore in either case the work would be 0. So 3 doesn't work. As he decelerates to a stop, well, he's still moving to the right, but now because he's slowing down, his force is going opposite of that direction. So this would be negative work. As with the 5th step here of lowering the boxes slowly to the floor, that would also be negative work as well. So then looking through my options, the only 2 that are correct are options 1 and 2, and therefore that makes D the correct choice for this question. Okay, so question 3 here is just a good one for relating our energies, right? The key is the fact that when you've compressed the spring, so the spring has a certain constant and it's been displaced this distance of x, regardless of which mass I'm using, whether it's m or 2m, when I compress the spring energy is based only on 1/2 the constant and x squared, right? So regardless of which mass is down here, the total spring energy and therefore the total energy of the system is the same for either situation, right? Because again, that's independent of the mass that's been placed there. So what that tells me is the total energy of each of my scenarios is the same. So then what that would tell us is if we're considering the total energy converts to kinetic energy down here, well, if I knew that they had the same kinetic energy, right, then I would just consider the fact that, so as I have 1/2 mass times velocity squared, well, if they have the same kinetic energy, if I were to double the mass, then I would have to cut the squared result in half. That doesn't mean I cut the velocity in half. That means I actually take the velocity and divide it by radical 2. That way when I square it, it ends up being cut in half, right? So keep that in mind. And then in terms of potential energy, as I look over here, right, again, I know that they have the same potential energy because by the time that they stop, all of their energy, which I knew was the same, all of their energy is now potential energy. So I know that their potential energies are the same. So if I look at that, mass times gravity times height, again, if I double the mass of the second one, obviously the acceleration of gravity doesn't change, so the height would have to be cut in half. And that ends up being my answer for this one. If I look through all of the options, they do try to distract us here with the just as it moves free of the spring, the lighter box will move twice as fast as the heavier box. Now again, it doesn't move twice as fast, it actually moves velocity times radical 2, not quite twice as fast. So B is probably the best distractor in there. But option A here is the best choice. The lighter box will go twice as high up, since if I know they have the final potential energy is the same. If I double the mass, I only go half the height, and therefore the lighter one goes twice as high as the heavier one. So option A again is the correct option on this problem. The key to question 4 is a very important one for us to realize, and that's the fact that again work relates to a change in energy. So obviously they give me some measurements here that helps with the kinetic energy. They give me the mass, they give me the speed. Once again, they give me the mass and the speed, right? Work relates to that change. However much work is done by this braking force, that's going to be its change of energy. So the reason that's important is because work is simply force times displacement, right, times my change in distance. And so if work is force times displacement, and I know that that relates to the change in kinetic energy, I know that they have the same force. So if I want to figure out which one goes further, I just need to figure out which one has a higher change in kinetic energy. So again, all we need to look at is what is their change in kinetic energy. Well, we know that they both come to rest, so the final kinetic energy for either one would be 0. So let's just look at the initial kinetic energy, right? So for my first object, it'd be 1/2 4 times the velocity squared. So 1/2 4 times 4. So it ends up being 8 joules of kinetic energy, and therefore I have to do 8 joules of work. But again, since the force is the same for both, we'll use that comparatively in just a minute. The second kinetic energy would be 1/2 1, right, for the mass times the velocity of 4 squared. So once again, it ends up being 1/2 of 16, so it ends up being 8 joules of kinetic energy. So each of these go from 8 joules of kinetic energy to 0. So they both experience the exact same change in kinetic energy. They both have the same force, the same braking force acting on them, and therefore the distance has to be the same for each situation. So option C is the correct option here. Again, they have to go the same distance since they have the same force and the same change in kinetic energy. So again, the key here, making sure you're comfortable with the relationship between work and the change in kinetic energy. Okay, so this question says, as the ball swings from the lowest point to the highest point, what is the work done by gravity and what is the work done by the tension? And it is very important we pay attention to which way it's going here, right? So as it moves from here up to the highest point, well, they give us the radius, right? They tell us the radius is 2 meters, and therefore we know the entire change in height here would be 4 meters. So my change in height would be 4 meters. The mass of the ball they gave me of 3 kilograms. So I can find my change in potential energy, right? I can find that change in potential energy. So my potential energy would just be mass times gravity times height. So 3 times 9.8 times my 4. Well, that ends up being about 118, which is why they're throwing that number around so much, right? So 118 joules of energy. So that's the change in energy from this lowest point to the highest point. Well, when we consider, though, the work done by gravity, we do have to consider the directions here. As the ball is moving upward, because the ball ends up displacing upward, right? So its change in position went upward. We know that the force of gravity is pulling downward. And therefore, as the ball moves upward, the force of gravity is doing negative work on the ball, right? Because the force of gravity is pulling down and the ball is moving up. So the work done by gravity is a negative 118 joules. So that kind of helps me figure it out. Now they do have most of the options with negative 118, although that helps me rule out C. And then that helps me rule out E, which says the work done by gravity is 0. So then it comes to tension. What's the tension doing, right? Well, they say the tension is taut and it's always perpendicular to the velocity. The key there is the fact that if the tension is always perpendicular to the velocity, if it's always perpendicular to the direction, we know that the work done by the tension would have to be 0, because if the force is perpendicular to the velocity or the direction, I know that no work is occurring. So the work done by gravity is a negative 118. The work done by tension would be 0, and therefore D is the correct option. The work done by gravity is 118, and then the tension of the string does 0 work. So anyway, that's our correct option for this choice here. So question 6 asks us to determine the directions of these two and then the angle between, right, the directions of those two. So probably the easiest way to do this is to just sketch out these two vectors, find their angles that they currently have, and then find the angle between them. And so what I mean by that is, so vector A, it tells us it's positive 3 and positive 1. So we know it's over 3, it's up 1. So here this blue vector is going to represent vector A for me. Again, it's going over 3 and up 1. Well, I can find that angle pretty easily just using some trig, right? So that's not a big issue. And then starting at that same origin, I'm just going to sketch out vector B. So vector B goes left 3 and then up 3. So I'll pretend that's up 3 there. So then this one, hopefully we don't even have to do the actual trig for it, right? We know it's going left 3, it's going up 3. Because those two legs are equal, I actually know that this needs to be then a 45-degree angle. So if I want to find the angle between these two vectors, well, I simply need to find then, right, this angle here between. So I know this is 45. I can do a little trig to find out what this angle is, right? So tangent of theta equals, this being theta 1 here, tangent of theta 1 equals 1 over 3, tangent inverse of that, and I get theta 1 equals about 18 degrees. So I know that this is 18 degrees, I know that this is 45, and I know that all three of those angles together would add up to be 180, so I don't even have to do any particular type of trig. I can just do 180 minus 45 minus 18, oops, minus 18 there, and then that ends up being about 117 degrees. So the angle between my two vectors, is 117 degrees. The reason it's important, the reason I threw this question in here, keep in mind when we do the dot product, the dot product says we'll take our vectors, we'll multiply our vectors, but then we will multiply the angle between them as well. So if we were doing our dot product algebraically, we need to know that angle between them. But anyway, hopefully this question wasn't too bad once you took the time to set it up. Question 7 here is also pretty easy as long as you know the definition of the dot product. Again, the dot product says you multiply the components of the vectors. So I take the x component of A times the the x component of B plus the y component of A times the y component of B. So as long as I'm comfortable with that, I'm just looking for which choice would give me a dot product that equals 10. So you kind of just have to guess and check a little bit here, but hopefully it's not too terribly difficult to do. Right? So 3 times 2 would be 6, plus 2 times 4, which is 8. So 6 plus 8 is 14. That one doesn't work. And again, I'm just going through until I find the one that works. So 3 times 4 is 12. 2 times 6 is also 12. 24 is too big. This one right here is definitely too big. 15 plus 8. Here this would be 3 times 0, but then 2 times 12 is 24, too big. And so my correct option is E. 3 times 2 is 6. 2 times 2 is 4. 6 plus 4 is 10. So hey, that one worked pretty well. So that was supposed to be a check mark. Let's try that again. There we go. Much better. But anyway, hopefully that one wasn't too bad as long as we're comfortable with the definition of the dot product. So then the last question we'll get on this first part here, just really getting comfortable again, finding the work done by various forces. Now this question is pretty nice because it breaks it up individually and just asks me to find the amount of work done by each of those forces individually. So if I want to find the work done by force 1, I'll call that the work 1, right? I just need to know what's force 1 times the distance. Well, they give me force 1 is 20, and force 1 is directed up the ramp, and they tell me that it moves a distance of 0.600 meters up the ramp. So it's just 20 times 0.6, again going up the ramp, and that ends up being 12 joules of work. So part A there, pretty easy, right? Hopefully not too bad. The work done by force 2, well, this one again not real tricky if you take your time with it. We know the displacement is up the ramp, so I'm only concerned with the component of the force that's going up the ramp. So that would be the cosine component, right, of force 2. So it's just going to be force 2 times cosine of theta times the distance that it goes up the ramp, which in this case force 2 is 40. Cosine of the angle which they give me is 30, and then again times that same distance of 0.6 because that's how far up the ramp it has gone. So my work 2 then is about 20.8 joules of energy, joules of work. Right? So again, hopefully nothing too tricky with that one. And then finally, part C here. Part C asks me what's the work done by force 3. Well, hopefully this was the easiest of all, right? We know that this force is pushing down, but we know that the block is moving up the ramp, so those two are in fact perpendicular. So if you're taking a force that is perpendicular to the distance, we hopefully all remember that that means the work is 0 joules, right? Don't fall into the trap of that one. Yes, they do give us numbers. It's not just 10 times 0.6 though. It is always 0. So anyway, I'll go ahead and stop the first part of the video here, and I'll pick up the last couple questions in part 2.